So far, the equations of motion and the analysis that we've discussed still are relatively idealistic. One thing we haven't thought about yet is friction. The reality is, when we go and derive the equations of motion, our systems don't oscillate, move forever. They do slow down. And the number one reason why they slow down is friction. We model friction by subtracting it from the right-hand side of our second-order differential equation. We subtract it because these forces impede the motion. Now, there are many models for friction. One model is the viscous friction model, where the amount of friction on your system is linearly proportional to the velocity of that system. Another friction model is Coulomb friction, where the amount of friction on your system is proportional to the sign of your velocity. In other words, the direction of your velocity. So it will impede motion by a fixed amount, but in the opposite direction that you happen to be moving. But even these two models, Coulomb friction and viscous friction, are still very idealistic. Another model of friction is something that we call stiction. I'm sure you all have the experience of when something is at rest, it takes quite a bit of force to get it to move, and then while it's moving, it maintains its motion. That's because you had to overcome static friction at first, and then to keep the object in motion, you're just overcoming dynamic friction. We call this stiction. So here it's modeled as, at first, there is an amount of, a higher amount of friction that you need just to get going, and then afterwards you have some lower quantity, but still friction. In this case, this is a stiction with Coulomb friction, where the magnitude in the opposite of the sign of direction is still lower than the magnitude that you need to get started.